Hello everyone and welcome to the next instalment in this series looking at standard level AA exam questions. Today's question comes from the trigonometry section of the syllabus. That's part 3 and it's to do with solving equations using trig ratios. Now I've given this one 3 out of 5 stars. It's only a short question, it's not too tricky, but it does involve a fair bit of knowledge from the syllabus, so that's why I thought we'd go through it today. So having a look and reading the question, there's a few things that we're going to draw our attention to straight away. The first is we have a show that in this first section. That should be a keyword that leaps out to you straight away, and it's essentially a kind of an informal proof. So here we're asked to show that the left-hand side of the equation is equal to the right-hand side. So we need to start with the left-hand side, follow a series of logical steps to arrive at the right-hand side. It's kind of like a question where they give you the answer, but you do need to be really careful and show all your steps. The other thing I noticed when I look at that equation a little bit more closely is that it's got a 2 theta in it. Now the minute you see 2 theta or 4 theta, a multiple of an angle, so double angle here, we know that we're going to need the double angle formula, so that's something you can look up in the formula booklet. And then we also see the word hence in the second part. That tells me that I'm really clearly going to use my result from the first part in the second. So even though that first part is only 2 marks, it's going to be significant. Now that's why they've done a show that as well. If you can't do the first part, for example, you can just use the result. So it's important to know that in questions, so you can dive back in even if you weren't able to do earlier parts. So let's get stuck in and see how this first part runs. Now, so here is part A, and I've also included the section from the formula booklet on double angle formulae. Now, the thing we've got to be conscious of here, if it was sine 2 theta, that's very straightforward. There's just one substitution. But for cosine 2 theta, there's actually 3 possible substitutions we can use here. And so you've got to think carefully about which one to choose. Now it's fairly obvious here. If you look at the left-hand side of the equation, we've got cosines and sines. On the right-hand side, we've just got sines. Okay, we have a sine squared. But what I want to do then is choose the substitution here that completely replaces cosine 2 theta with only sines. So it's not going to be this one, it's not going to be this one. It has to be this last one, 1 minus 2 sine squared theta. Now, it is a show that question, as I said, so what we want to do is we want to start working with the left-hand side. Now, LHS is just a common abbreviation, you can use that in your work. And we'll start with the left-hand side, which is 4 minus cos 2 theta plus 5 sine theta. And I'm going to use the double angle formula to replace my middle term with, as I highlighted, the third substitution. Now, I'm just going to be a little bit careful and use a bracket for this. The reason I do this is just to help make sure that I don't make any mistakes with my signs, that is the plus minus signs, because I've got a negative term and it's then I'm substituting a negative in. I just want to ensure that I don't make any mistakes there. But again, the beauty of a show that question is I know what the answer should be, so if I make a mistake I can always just sort of go back and change my working. So pretty easy from here. We're just going to replace that with negative 1. We get minus 2 sine squared, so plus 2 sine squared theta plus 5 sine theta. Now what I'm going to do is just rearrange this in descending powers of sine, just like you would with a normal polynomial, and we're going to end up at 2 sine squared theta plus 5 sine theta plus 3, which is equal to the right hand side as required. So when you're doing a show that question, you just want to finish off by showing you have shown what you were asked to. And that's the first part done. Nothing too tricky, so long as you choose the right substitution from the double angle formula. Which brings us now on to part B. Again, the word hence is in there, and this is telling me that I need to use the result from the last section. So hence solve. Now this equation, again, we've got cosines and sines on the left-hand side. That's going to make it a little bit harder to solve, so I use the result from the first section and replace the left-hand side of this equation with the right-hand side from the result from part A. So we have 2 sine squared theta plus 5 sine theta plus 3 equals 0. Now, what we've got here is a quadratic in sine theta. And what I encourage my students to do when we have this sort of setup is actually to use a dummy variable to make the quadratic just look more like the ones you're used to solving. In this case, we're just going to use x equals sine theta. Again, it's just a dummy variable here, there's no significance. Just want to make sure you don't choose something that's already been used in the question. So if x has already been used in the question, go for another letter. And simply rewrite the quadratic now as 2x squared plus 5x plus 3. The only reason to do this is just so it's more familiar, and I guess you're less likely to make a mistake. So looking at a quadratic now, we know that we need to factorize. We've got a leading coefficient of 2, which makes it a little bit tricky, but not too hard, since there's only one way to factorize 2x, that's 2x and x, and there's only one way to factorize 3, that's 1 and 3. Now what I'm looking for is I need to multiply one of the factors by 2x and the other factor by x to make 5x's in total. So I think the way I'm going to do this one is have a 3 here and a 1 here. I know they both need to be positive because the 3 is positive. And if I look, I get the outside product is 2x, the inside product is 3x, giving me a total of 5x. So there we go, we factorized, and by the null factor theorem now, we can turn this into two different equations. The first one tells me, well, the only way these things can be 0, the product can be 0, is if either of them, or at least one of them, is 0. So either x plus 1 equals 0, which gives me the solution x is negative 1, or 2x plus 3 is equal to 0, which gives me the solution x is negative 3 over 2. Now, one of the things you have to be really cautious with when doing trig equations is that you account for all your solutions. You don't lose any. So particularly when you think of doing something like square roots, people often only take the positive square root, but you also have to make sure you explain away why you're discarding some solutions. So you might already think we want to get rid of that solution. It's not actually going to lead to any solutions, but let's just follow it through and be really methodical about how we do that. So we use the dummy variable x, which was sine theta. So I'm just going to turn these two equations back into equations in terms of sine theta. So we had that sine theta is equal to negative 1, or sine theta is equal to negative 3 over 2. Now, that set of solutions here, there are no solutions, simply because sine can only take values between negative 1 and 1. We're just going to write a quick note to the examiner to say that's why we've discarded this. It's really important you do that, just so that they don't think you've just ignored part of your work. So we'll just say since sine has to be between negative 1 and 1. The more things you can do like that, just leave little notes for the examiner to convince them that you know what you're doing, the better, the more likely you are to get your method marks here. So no solutions from that section, and we're simply left with sine theta is negative 1. We need to turn that back into an angle, so to give our value of theta. Now, whenever you're doing an angles problem, you always have to ask yourself, well, do I need to give my answer here in degrees or in radians? If we flip back to the question, the clue is normally in the question, and you can see here, hence solve, and it gives us a range of for theta in radians. So we're going to make sure we give our answer in radians. So if sine theta is negative 1, what is theta? Well, there's a couple of ways you can address this. The first is by using a sketch of the graph. Now I say sketch, and I mean sketch, you really just have to do this very roughly. It's not about having a beautiful picture, it's just about an aid for your thinking. As we said before, sine goes from 1 to negative 1, and so you can see that the only place on the graph where I have a sine value of negative 1 is here, and that's at either 270 degrees or 3 pi by 2 radians. Remember, the easy conversion here is that your 360 degrees is 2 pi radians, or 180 degrees is pi radians, and from there you can just sort of reason and convert. So 3/4 of the way along, 3 over 2 pi. That's the one way we can think about our solution. The other, of course, is to use the unit circle. I find this is quite a personal preference thing. Some people much rather think about graphs, some people much rather think in terms of the unit circle. But again, remembering sine is on the y-axis and cosine is on the x-axis. There's only one place that has a y-axis value of negative 1, and that's around here. So I'm turning this full angle around here, again 3/4 of a full turn, or 3 pi by 2 radians. And so there is our only solution in this problem, 3 pi by 2. The things to be conscious of here, I think, are just being really clear with your method. It's not good enough just to find that one solution. You really do want to show how you arrived at that solution and why you discarded other solutions along the way. And that's it for today. Thanks very much for listening.